Hey, this is lecture number 9, and after we have done a crash course on polyhedral combinatorics, this is going to be my next crash course, this time on computational complexity. So let's see what we are going to do in this lecture. So that is essentially the definitions of P, NP, and co-NP complexity classes, and the most powerful tool in computational complexity, namely that of problem reductions. In terms of technical depth or difficulty, I think this lecture is going to be much, much lighter than the previous one on polyhedral combinatorics. So in order to define the complexity classes P, NP, and co-NP, we first of all need to define what decision problems are. And to begin with, we have to remember what we define to be an efficient algorithm to solve a combinatorial optimization problem. So this pi here denotes some combinatorial optimization problem. And we called an algorithm efficient if for every instance of that problem, so instance I of that problem pi, the computation time of the algorithm was bounded by a polynomial function in the size of the instance. And here the size always denotes the encoding length of the instance. So we assume an efficient encoding length of the instance. Just to give an example, if you think of the shortest path problem here, the encoding of the problem was in terms of the graph and the edge length and not as a list of all the possible ST paths, right? So that's what I denote with an efficient encoding of the problem. So these are 3 examples of problems for which we could show that these problems have efficient polynomial time algorithms to solve them. So that was Dijkstra's algorithm for the shortest path problem. For example, the pre-flow push algorithm to solve the maximum flow problem, or Edmonds' algorithm to solve the matching problem. Now, these are optimization problems, and what is a decision problem? So a decision problem, in the name, it already says it, it's a problem which has 2 possible answers, yes or no. And that's exactly what we do. So we define a decision problem pi, that's a set of instances, a collection of instances of that problem, that are really partitioned into 2 classes, yes or no instance, and they are denoted by this curly I yes, that's the yes instances, and this curly I no, that's the no instances, such that this is a real partition. So every instance is either yes or no, and no instance can be a yes and no instance at the same time. Okay, so let's look at some examples of that to make that a bit more practical. So if I say my instances are in all integer matrices, okay, then I could say, okay, all the yes instances, that's all the integer matrices which are totally unimodular. And then the no instances, and the no instances would be the ones that are not totally unimodular, and this is mutually exclusive, right? Every matrix is either TUM or not. Or if all my instances are the natural numbers, yes instances are prime numbers and no instances are composite numbers. Instances could be undirected graphs, and then we say yes instances, that's those graphs G which do have a perfect matching, so far, where all the nodes of the graph are actually matched to a neighbor. Another example, final example, again on undirected graphs, the yes instances would be those that do have a Hamiltonian cycle. Just to recall what that problem is, a Hamiltonian cycle is a cycle that visits all the vertices of the graph exactly once. So here's a simple little example of a graph, and in blue you can see a Hamiltonian cycle of the graph visiting all the vertices, right? So that's the problem that underlies the famous traveling salesman problem, where you also have costs or lengths on the edges, and you want to find such a Hamiltonian cycle of minimal length if there exists more than one. And for the sake of completeness, let's just briefly have a look at an integer programming formulation for the Hamiltonian cycle or the traveling salesman problem, where we use decision variables x of e, which are 1 if an edge is selected to be in the Hamiltonian cycle and 0 otherwise. And then if we have costs on the edges, we, for example, would like to minimize the total length of such a tour. And now we have to set up constraints that make sure that the selected edges actually represent a Hamiltonian cycle in the graph. And how do we do that? Well, first of all, it should be clear that if I look at all the edges incident to one particular node V, so all the edges E in the cut induced by V, then I will have exactly two of those, right? So if I look at an edge, I'm actually entering it and exiting it exactly once. So that means that the number of selected edges incident to such a node V, that should be exactly 2. That's almost the formulation, but now we could still have the situation that we select, for example, 2 cycles in the graph, which are independent from each other. So we have to forbid that, and that is the so-called subtour elimination constraints, which says that if I look at the edges of any particular cut in the graph, so all the edges delta of S for a subset of the nodes S, and the selected edges, then I have to enter that set and exit that set at least once. So that makes at least 2 edges from the cut. It could be more than that. So for this example here, if that is the set S, then this set of vertices would violate this subtour elimination constraint, right? So, and that should be true for all non-empty sets, not equal to the whole set of edges. And of course, the variables should be either 0 or 1. And that's already a description, an integer programming description of the traveling salesman problem, or the decision version existence of such a tour could be modeled like that. Okay, so this was our first definition, decision problems, which is a collection of instances which are either yes or no. But how does this relate to the problems that we're actually interested in, namely optimization problems? And that goes very naturally. So remember that an instance of an optimization problem that consists of a set of feasible solutions to that instance, and then each feasible solution has a certain cost or objective function value which we would like to minimize, say. Okay, so we are interested in the feasible solution with minimum total cost. And the corresponding decision version just asks the question, does there exist a feasible solution which has cost at most k? Or in other words, is the optimum solution value at most k, yes or no? Okay, so the corresponding decision version of the problem is, given an instance of an optimization problem and some threshold value k, I call an instance a yes instance if there exists a feasible solution which achieves a value at most k. So, which is equivalent with saying that the optimum objective function value is at most k. Okay, so the yes instances would be all the instances that do have feasible solutions with value at most k, and the no instances would be all those where all the feasible solutions have a value at least or strictly larger than k. And then this is mutually exclusive, and we have partitioned all the instances of the optimization problem into yes and no instances. So a couple of examples. For example, for the matching problem, we also, given a graph, bipartite, non-bipartite, and an integer k, we would ask, does the graph have a matching of size at least k? Because this would be a maximization problem, yes or no, right? And in this way, we can partition the graphs into those that do have a matching of size at least k and those that don't. In the traveling salesman problem, we would ask or partition the set of instances into those that do have a Hamiltonian cycle of cost at most k and those that don't. And also for minimum cost flow, the same thing. Does a given flow network have a feasible flow of cost at most k? Yes or no? Same for linear programming, for instance. So here the feasible solutions are all the vectors x and Rn, which fulfill all the linear constraints. We have a linear objective function and some threshold number k, and an instance is now a yes instances if there exists a feasible solution that achieves an objective function value at most k. Now, since we are going to restrict to decision problems from now on, at least for this lecture, the question is that a loss of generality, yes or no? And the bottom line will be no. The restriction to decision problems instead of optimization problems is generally not any loss of generality. So what I mean precisely is the following. One direction here is obvious. Suppose we have an efficient algorithm to solve an optimization problem, like shortest path or matching problem. Then this, of course, also yields an efficient algorithm to solve the corresponding decision problem for any k, right? Because we can just use that optimization algorithm in order to find, say, the maximum matching in the graph, and then we can say, oh yes, this is an instance where there exists a matching of size at least k, right? So this direction is trivial. But suppose now that we only have an algorithm to solve the decision problem for any value of k, okay? Can we also get an efficient algorithm to actually solve the optimization problem doing that? And the answer is going to be yes, this is true. For all of the optimization problems that we have been talking about, and there is only very few exceptions, which I'm not going to go into details in this lecture. Okay, so the takeaway message will be that considering decision problems with respect to the existence of efficient algorithms to solve them is no loss of generality. So how do we see that? How do we convince ourselves that if we have an algorithm that can solve the decision version of the problem in polynomial time, that then we can also solve the optimization version of the problem in polynomial time? And the answer to that question is binary search. Okay, so we do binary search to first of all find the optimum solution value, and then knowing that, we can actually also find the optimum solution itself. So let me illustrate that on the example of the matching problem. So we do binary search to determine or to find the optimum solution value, which is denoted psi here. And remember that for the matching problem, well, what is the size of a maximum matching? That can be at most n halves, essentially. Okay, so we start out with the knowledge that the optimum solution value will be between 0 and n halves. Okay, and we have this algorithm that can decide, does there exist a matching of size k or not? Or does there exist a matching of size k halves or not? So what we do is we consider the whole interval which contains the optimum solution value. We ask our algorithm, does there exist a solution of value at least k, yes or no? If the answer is yes, we continue searching for the optimum solution value in the blue part of the whole interval. If the answer is no, we continue searching on the red part of the interval. And notice that if we divide the whole interval length always in equally sized parts, the size of the interval in which we search the optimum value will have decreased by a factor of 2. Okay, so that means after log k or log n halves many iterations or calls of this algorithm, we will have found the optimum solution value psi. Okay, so here is the corresponding pseudocode for that procedure, for that binary search procedure. So we assume we have this algorithm that always can tell us, does there exist a matching of size at least k, yes or no? And the binary search goes over the search interval for the optimum solution value, which must lie between 0 and essentially n halves, right? And what we do in each iteration, we cut the interval into equally sized parts, essentially up to rounding. And then we determine, by using this algorithm, we determine if we have to continue in the right part of the smaller intervals or in the left part, right? And well, as I said, after log n many iterations, we will have found the optimum solution value. And this is still a polynomial computation time, because we assumed that our algorithm to solve the decision problem was a polynomial time algorithm. So now we know the optimum solution value. So we know the size of the maximum size matching. How do we find the solution itself? Well, knowing the optimum solution value, finding the solution is also easy. We go over all the edges of the graph, and then we ask, well, is the answer still yes? Does there still exist a matching of the optimum maximum size if I remove the edge E? And if the answer is yes, I can delete this edge E from the graph, right? Otherwise, I have to keep it in. And after I have gone over all the edges, I return the remaining edges, and this will be a maximum size matching. How often did I have to call this algorithm here in this second part? Well, I went over all the edges, which is still a polynomial, and that often I called the algorithm, which was also polynomial time. So in total, the whole computation time is still polynomial. So I have called this procedure to solve the decision problem a polynomial number of times, and I have actually solved the optimization problem doing that. So once again, the bottom line is that restricting to decision versions of optimization problems is mostly without loss of generality when it comes to computational complexity or the existence of efficient algorithms. I showed you one example for matching, and for all problems that we are talking about, more or less the same can be done. Okay, so that was the first ingredient. So we know, or we have convinced ourselves, that the restriction to decision problems is no loss of generality. The next concept that we need is that of certification or certificates. So the idea here is, if somebody claims there exists a matching in a graph of a certain size, how can this person prove it to me, and how can I efficiently verify that this proof is correct? So this is about succinct proofs of optimality or proofs of existence. Okay, so let me give an example. Consider the bipartite matching problem to start with. So how would you certify to me that a graph G has a matching of a certain size K? Well, that's very simple, right? You just exhibit this particular matching M that is large enough, that has size at least K. And if you show to me, if you tell me which edges are matching edges, I can also verify your claim efficiently, right? So I just go over the whole graph and check if the edges that you told me are indeed, if that is indeed a matching. So I have to verify all the degree constraints, and I have to check that the matching has the right size at least, right? So that's very easy. Now, how would you certify the opposite? How would you certify that a graph has no matching of a size K? And also that can be done. We only have to know a little bit of the theory. So we have to know Koenig's theorem. That was a theorem about matchings or size of matchings in bipartite graphs, which is equal to the size of a node cover or minimum node cover in the same graph, right? So if you want to certify to me that the graph has no matching of size K, you just tell me, okay, I give you this node cover U of the graph, and it has a very small size, namely at most K minus 1. And I can verify that this is true. I can verify that what you give me is indeed a node cover of the graph in linear time in the size of the graph. And by Koenig's theorem, I know that the size of a maximum matching is equal to the size of a minimum node cover, which means that for all matchings, the size of that matching is at most the size of the node cover that you gave me, which had size K minus 1. So I know that for all the matchings, they must have size at most K minus 1. Okay. In other words, there exists no matching of size at least K. So the matching problem for bipartite graphs, or more precisely, the decision problem, does there exist a matching of a certain size K in a bipartite graph, has these two very nice properties. That is, for yes instances, there exists a certificate that can be verified efficiently in polynomial time, and for no instances, there also exists a certificate which can also be verified in polynomial time. And problems which have this property namely that yes and no instances have certificates which can be verified efficiently. That's a very nice property. And Edmonds called such problems with a good characterization. So a problem with a good characterization, he called this as those problems where yes and no instances have certificates which can be checked efficiently. So that was not so difficult for the bipartite matching problem. And as a side remark, what happens if we consider the matching problem in general, non-bipartite graphs? So how would I the certification of yes instances is still simple. It's exactly the same. But how do I certify no instances? And there I have to be a little bit more careful. So for instance, look at this trivial example graph again, the smallest non-bipartite graph, the triangle. And we know that all the matchings have size 1, smaller than 2, right? But we cannot find a node cover of size 1 to certify in exactly the same way as we did earlier that there exists no matching of size 2, right? So what do we do here? And the idea is, well, if you remember from last lecture, the matching problem has a linear programming formulation if we add these so-called odd set inequalities. Okay, so we consider this linear programming formulation that we had in the last lecture for the matching problem. So that's maximize the number of edges you select, subject to the constraint that every vertex has degree at most 1. And we had added these so-called odd set inequalities here, which says that if I have an odd set of vertices, I can have at most that many matching edges inside that set, right? And this formulation or the corresponding polytope here had integer vertices, which again correspond to matchings. And now I can just use general duality theory in order to certify the non-existence of certain solutions with a large value for this primal. Now the primal is a maximization problem, the dual is a minimization problem, and I just have to exhibit a feasible dual solution, a solution to the dual of this linear programming formulation to prove non-existence of primal solutions of large size or large value. So what is the dual? In the dual, we would have variables yv, which correspond to these degree constraints, and ys, which is the variables that correspond to the odd sets of vertices. And back to our small example here, we only have precisely one odd set, namely that's all 3 vertices together. And the corresponding dual to this formulation here appears up here. Okay, it's a minimization problem. It is almost the same as the node cover formulation that we had in the last lecture. So these are the variables corresponding to the nodes of the graph. So I select nodes in the graph, but now I also select odd sets. Okay, so I minimize the total sum of these variables here in the corresponding dual, and the constraints, that's constraints for the edges of the graph, namely that I have to select at least one of the 2 endpoints, and these constraints now also involve these new dual variables for the odd set. Okay, and if you look at this LP just as an LP, you see that there is a feasible solution where you set this variable equal to 1, thereby fulfilling all these 3 constraints here, and it gives you an objective function value of 1. So we have a feasible dual solution which has an objective function value of 1, and therefore we know that the primal problem can have no objective function value larger than that. And that's exactly what we have been looking for, namely the proof that there is no matching of size larger than 1. Okay, so that was a small side remark for the non-bipartite matching problem and certification of no instances. Let's go back to other problems. So for example, maximum flow. Okay, so given a graph with say integer edge capacities and ST, how would you certify to me that this graph has a flow of value at least k? And again here, the answer is simple. You just give me the flow values per edge, And I can verify in linear time in the size of the corresponding graph if this is really a feasible flow and if the value is at least k. Okay, so again, yes, instances can be certified and the certification can be checked efficiently. So how would we certify that there is no flow with a value at least k? And also here we had a duality theorem, namely that involving minimum cuts, right? So you just, if you want to convince me that there is no flow of a value k or larger, you just show me a cut which has a capacity at most k minus 1. And then I know by the maximum flow minimum cut theorem that no flow value can be larger than this k minus 1. And also that can be verified in linear time in the size of the network. So verification that this is indeed a network cut. And the capacity of the cut can also be computed easily. Okay. And knowing the max flow min cut theorem, I know that this is a valid certificate, a feasible certificate to prove that there is no flow with that value k. Okay, so also the maximum flow problem has a good characterization in the words of Edmonds. So next problem, just general linear programming. And I think it's already clear what is going to happen. So if we consider a standard LP, say minimization problem here, minimize a linear function, and here's a feasibility region defined by these constraints, ax less or equal than b, and x non-negative. Then the corresponding decision problem would be, is the optimum solution at most k, right? Or in other words, does there exist a solution of value at most k? And as usual, certification of yes instances, you just show me or give me the solution that achieves a value at most k. And then I know that the optimum solution value will be at most k. What is the certification for no instances? Same way like we did it for the general matching problem. You give me a dual feasible solution y. So dual feasibility is here, which has an objective function value larger than k in this case, because it's a minimization problem. So if the dual solution value is larger than k, okay, so k is smaller than the dual solution value. Now I invoke the weak duality theorem, or here the primal feasibility, namely that b is at most ax, or ax is larger or equal than b. And here we invoke dual feasibility, and then we see that our primal solution value for any feasible primal solution will be strictly larger than k. Okay, so there exists no solution smaller or equal than k. So this is our certification of non-existence of solutions of value at most k. So also linear programming has a good characterization in the words of Jack Edmonds. So since this was reasonably simple, let's just move on to the next problem on our list. And that would be the Hamiltonian cycle problem. So existence of so the decision problem is, does there exist a Hamilton cycle in a given undirected graph, or does there exist a Hamilton cycle with a certain length or with length at most k in a given graph? That would be the traveling salesman problem. And once again, the certification for yes instances is simple by just giving me the corresponding solution. So you just give me the corresponding Hamilton cycle, and I can verify efficiently that this is indeed a Hamilton cycle. And I can also compute its length if the edges have lengths, okay? But the certification of no instances is a bit more problematic here. So how do we certify non-existence of a Hamilton cycle in a graph? What we are lacking is this nice kind of duality theorem that we were using in all the previous examples, right? So for no instances, essentially, we don't know what to do except for maybe giving me a list of all the possible orders of the nodes of the graph and then checking that none of them corresponds to a Hamilton cycle. So certification of no instances for the traveling salesman problem or Hamiltonian cycle problem is a bit problematic, it seems. So one possible way of doing it is giving me all the lists of different orders of the nodes of the graph. Like if we have this little example here, a graph on 4 nodes, then I can, of course, pick an arbitrary starting vertex, say vertex number 1, and then I can consider all the possible orderings of the remaining vertices of the graph, right? And since it doesn't matter if I go through the graph like this or in the other direction, I can also divide out half of these orderings by symmetry reasons. So I would have to write down a list of all the possible different orders, and for a graph on 4 vertices, that would be 3 different orders actually. And then I can verify that none of them would correspond to a Hamilton cycle in the graph. So here in this example, there exists a Hamilton cycle, but if I go over all these orderings here and none of them corresponds to a Hamilton cycle, then I would be convinced that no Hamilton cycle exists in this graph. So that is nice. We can certify no instances, but it's a bit problematic in the sense that the size of this certificate could be exponentially long, right? Because this is essentially n factorial many orders that I have to consider. So that's of the order at least 2 to the n. So that's too many to check efficiently, at least, efficiently meaning in polynomial time. So for the Hamilton cycle or the traveling salesman problem, the only certificate that I can come up with has exponential size. All right, so we have seen a handful of problems for which it was even possible to certify efficiently both yes and no instances, okay? And the examples that I went through, that was the maximum flow problem, that was the matching problem, and linear programming. And this list could be extended a little bit further. So it would also include shortest path problem, for instance, or minimum spanning tree problem, and also the minimum cost flow problem. So that's all problems for which certification of yes and no instances is possible. Efficient certification. On the other hand, we have seen the Hamiltonian cycle problem for which at least we could certify yes instances, but no instances were problematic in the sense that the one that we came up with had exponential size. And as a matter of fact, this list of problems can be extended almost indefinitely. So all these problems here have efficient certification of yes instances, but most probably no efficient certification of no instances. And this observation that there is a whole bunch of problems which at least have one of these two nice properties, namely for the yes instances, that gives rise to the definition of corresponding complexity classes, which eventually will be the classes NP and co-NP, and also P for polynomial time solvability. And the first class that we are going to define is the complexity class NP for non-deterministic polynomial time, which includes all the problems that I had on the previous slide. Okay, so that's the definition. A decision problem pi is member of NP. That's decision problems that can be solved in non-deterministic polynomial time. And that means that every yes instance has a certificate X, and the validity of that certificate can be verified in time polynomial in the input size of the problem. Okay, so this certificate can really be thought of as a proof for the instance indeed being a yes instance, and all the problems on the previous or second to previous slide fulfill this property. So let me be a bit more precise what that means. So what I mean is, what does it mean to verify a certificate in polynomial time? So that means that for all yes instances, we have the certificate X and the algorithm, such that the algorithm, given the instance and the certificate, returns yes, if and only if the instance indeed was a yes instance. Okay, so it's required that this algorithm runs in time polynomially in the input size for all yes instances. And in that sense, the algorithm verifies the validity of this proof X for yes instances because it returns yes if and only if the instance was a yes instance. Okay, so that is the definition. And a few notes. So nothing really is required for no instances, not even that the algorithm runs in polynomial time for no instances, where nothing should be maybe specified more precisely. Our verification algorithm should not return yes when the instance is a no instance, right? So for all no instances, our verification algorithm either doesn't terminate at all, for instance, but it certainly doesn't return yes after polynomially many steps. Okay, so that is still part of the definition, that the verification algorithm is able to verify validity of instances for yes instances. Also, nothing is required about the computation of this proof, this certificate X. Okay, so it is just given. So if only the existence is required, but not that we can compute it in polynomial time, for instance. And the polynomial time verifiability of this certificate X implies that the size of the certificate can only be polynomial in the size of the input instance. Okay. And as I already said, for all problems from the previous slide, all problems are part of this complexity class NP. And the certificate in most of the cases is just the corresponding feasible solution that achieves a certain value. Okay. All right, so that was the definition of the most important complexity class in this lecture, non-deterministic polynomial time. I will say a few words about the name in a minute. But first, let us define the other side of the world. So that's the complexity class CoNP. And that is exactly the same definition, only that now we require that every no instance has a certificate whose validity can be verified in time, polynomial in the input size of the instance. Okay. Otherwise, the definition is totally symmetric. So nothing in quotes is required for yes instances. Nothing is required about the efficient computation of the certificate. And also here, the certificate has a size that is polynomially bounded. Now, CoNP is maybe a bit less natural at first sight, so let me at least present you two problems that are very naturally seen to be member of this complexity class CoNP. And the first one is the property of being a totally unimodular matrix. Okay, so given an integer matrix A, the question is that matrix totally unimodular? And the possible answers are yes and no. So if you give me a no instance, a matrix that is not totally unimodular, you can verify, or one possible certificate for verification of the no instance is just a square submatrix B, which has a determinant which is not equal to plus or minus 1 or 0. Okay. Remember, the total unimodularity means that all the square submatrices must have determinant 0, plus or minus 1. So certifying a no instance, a non-total unimodular matrix is very simple by just giving such a square submatrix. Now, one word about verification of this certificate. Certainly the certificate is polynomial in the size of the original problem. It's just a submatrix. So that is clear. But we need to be able to verify that the determinant of the submatrix is indeed something else than 0 or plus or minus 1. And we have to be a bit careful here, because most probably the algorithm that you think of that you use when you compute determinants, that is this Laplace procedure. So you develop the determinant according to one row or column of the matrix. And that is what is happening here, okay? But this is a recursive procedure which takes exponential computation time, right? So because we compute k times a subdeterminant of a matrix of size k minus 1 times k minus 1, and then we iterate that procedure, and that in total is an exponential computation time. So we have this succinct certificate here for no instances, but the verification is a bit less trivial. And I just mentioned that this is possible in polynomial time. So computation of the determinant of a matrix is not a difficult problem. It can be solved in polynomial time. So for instance, in time n to the 3, where n is the size of the square submatrix, so n times n, by using a so-called LU decomposition of the matrix B. Okay, and an LU decomposition is just a decomposition of the matrix B into two matrices L and U, where L is a lower triangular matrix which has only zeros above the upper diagonal, and U is an upper triangular matrix with only zeros below the diagonal, and the determinants of such matrices L and U, that is just the product of the diagonal elements. And the computation of such an LU decomposition, that can be done in time n to the 3. Okay, so that proves that total unimodularity rather easily can be shown to be a part of this class co-NP, complement NP. And as a matter of fact, it can also be shown to be a member of NP, but that is more difficult and I'm not going to comment on it here. So let's rather look at another example, another very natural member of the class co-NP, and that is the problem primes. So the problem is a number, a natural number, and the question is that number a prime, yes or no? And also here, for no instances, we have a very simple certificate, right? A no instance is just a composite number, so it has divisors. So the certificate for a no instance is then just some divisor of the problem. So you just give me a factor x, such that n is a multiple of x, okay? And then I have to be able to verify that this is really true, but also that is not so difficult. So first of all, by definition, this number x, which is a divisor of n, that is a number smaller than n, so the certificate certainly has polynomial size, and we need to be able to verify that n is a multiple of x. And for that, we can use the school book algorithm that you probably did already in primary school. So you have to compute n divided by x, that's integer division, okay? And this algorithm is an algorithm that works digit by digit. And the whole procedure is actually quadratic in the logarithm of the number n. And that is a polynomial in log n. And that is also something that we need here because we have to be a bit careful about the encoding length of this problem. So the problem primes, I mean the instance is just a number, and the encoding length of an instance is just logarithmic in the size of the number, right? It's just log n. So if we want to have an algorithm that verifies the certificate at polynomial time, we have to be able to do that in time polynomial in log n and not in time polynomial in n. But the schoolbook algorithm actually does that. So I presented these two examples, total unimodularity and primes, in particular also to convince you that this class co-NP for complement NP also has very natural members. All right, so let's go back and look at this Venn diagram. So we have defined a complexity class NP. That were problems that have, for which yes instances have a certificate that can be verified efficiently, and we have defined co-NP. That was the same for the problems for which no instances have such a certificate. And in the beginning of the lecture, we have looked at max flow, bipartite matching, and linear programming. And all three problems had certificates for yes and no instances by duality arguments, right? So that means that these three problems and some others are actually both in NP and in co-NP, hence they lie in the intersection of NP and co-NP. Other problems that we have looked at was the Hamiltonian cycle problem, which was certainly a member of NP, and we have looked at the problems primes and total unimodularity, which were examples of co-NP problems. But first, let us concentrate on this intersection of NP and co-NP, because as a matter of fact, for all these problems, max flow, bipartite matching, linear programming, we not only know that they lie in NP and also in co-NP, but we even had polynomial time algorithms to solve them. Okay, and that is of course not a coincidence. So as a matter of fact, for all the problems for which we have polynomial time algorithms, we can argue that all these problems lie in the intersection of NP and co-NP. And that is actually going to be our first little theorem in complexity theory. But first of all, in order to formulate it, let us recall or define the complexity class P for polynomial time solvability. So we say that a decision problem pi is member of the class P for polynomial time solvability if there exists an algorithm that runs in polynomial time for any input instance, and it can determine for any input instance whether the instance is a yes instance or a no instance. So that means solving a decision problem, being able to determine the right answer, yes or no, in polynomial time. And the theorem, before the theorem, just one more remark. So that means that the algorithm actually returns yes on an instance I if and only if this instance is a yes instance, or it returns no if and only if the instance is a no instance. And now the theorem, which doesn't come as a big surprise now, is complexity class P for polynomial time solvability that's a subset of NP and co-NP. And for a proof, we essentially do the following trick. So in both cases, so we have to show two inclusions, right? P is a subset of NP and P is a subset of co-NP. We just take the empty certificate. Because if we have a problem in P, we can just decide in polynomial time if an instance is a yes or no instance, independent of any certificate, right? So just taking an empty certificate just does the job. And more formally, to show that P is a subset of NP, what I have to show is that yes instances can be verified in polynomial time. So if you give me a yes instance, then I just take my algorithm, which decides the problem. So it decides for any instance if it's yes or no. And hence I can just append to the input an empty certificate, which is useless. And the algorithm will correctly decide yes in polynomial time for this yes instance. And the same actually for no instances. And that works because this algorithm actually returns yes if and only if the instance is a yes instance. So it returns no if and only if the instance was a no instance. So we can go back to our Venn diagram here and complete this Venn diagram by saying that the polynomial time solvable decision problems are actually a subset of NP and also a subset of co-NP. So they lie in this intersection. And you, of course, notice that this is some darker green and this is just a light green. So the question is there also something here? And the answer is yes. But before I turn to that question, just a little remark. Since, we have had in this lecture polynomial time algorithms for maximum flow, also for bipartite matching, but what about linear programming? We didn't really treat algorithms for linear programming in this lecture. As a matter of fact, the simplex algorithm, which solves linear programs, is not a polynomial time algorithm. But at the end of the 70s, it was actually Kacchian who proposed an algorithm which is known as the ellipsoid method, which does solve linear programming problems, at least theoretically, in polynomial time. So hence, indeed, linear programming is not only in NP and co-NP, but it's even in the class P. Okay. Now, I was asking the question if there is also something in between here in this light green area, and the answer is yes. So for instance, when I was still a PhD student at the end of the 90s, it was the problem primes that was known to be in NP and co-NP, but not known to be polynomial time solvable. So as a matter of fact, back then, the problem primes was located here. We already did the proof that it is a co-NP problem a couple of slides back. And there's a theorem by Pratt from 75 that also shows that the problem primes is a problem which lies also in NP, so it's an NP and co-NP, but it was not known to be polynomial time solvable. And while I was a PhD student, the paper then appeared in 2002. Agrawal, a professor in India, together with two bachelor students actually, was able to show that there exists a polynomial time algorithm to decide if a number is a prime or not. So this problem actually has moved into the sweet spot here of polynomial time solvable problems. And as a matter of fact, determining if P is just equal to the intersection of NP and co-NP would solve one of the major open problems in complexity theory. Okay, so if you would be able to solve that, you would be instantaneously world famous, at least in the corresponding communities. At the moment, we are not that far, and there are still problems, at least a handful, which are known to be in this intersection in NP and also in co-NP, but not known to be polynomial time solvable. And one of these problems, which plays an important role in the cryptography, is integer factorization. And in integer factorization, we essentially ask for a small divisor of a given number n. So given is a number n, for which we seek a divisor, and given is some threshold number m smaller than n, and we ask if there exists a divisor which is at most m. Okay, so that is the problem. Integer factorization is known to be an NP and co-NP, but not known to be polynomial time solvable. So let me finally say something about the name non-determinism. So why do we call this class NP for non-deterministic polynomial time? Because the class P, that is exactly deterministic polynomial time. So how do these things really compare? And one way of thinking about it is the following. Suppose we guess one of the certificates, and let's say we talk about a subset selection problem. So that means a certificate would be a subset of the nodes or a subset of the edges, something like that. Okay. And if we are talking about a yes instance, we know that there exists a certificate such that the verification turns out to be successful. And that means if we guess a certificate, we have a non-zero success probability. Whereas talking about a no instance, the verification will always return no, or at least it will never return yes. So the success probability of the verification of the certificate is then equal to 0. So we can separate yes and no instances by success probabilities strictly larger than 0 and success probabilities equal to 0. And that is how a non-deterministic polynomial time algorithm solves the problem. It is just possible to guess the right certificate, or in other words, we say that such an algorithm solves the problem if the success probability is strictly larger than 0. So once again, if you give me a yes instance, there at least exists a certificate such that verification turns out to be successful. And that means we have a non-zero success probability, right? Whereas if you give me a no instance, the verification algorithm will never return yes. And if you compare that with the class P for polynomial time or deterministic polynomial time solvability, here we ask even more, namely if you guess a certificate or give me a random certificate X, if it is a yes instance, the algorithm always have to return yes, right? So that means for a random certificate, the success probability is equal to 1. So in polynomial time solvability, we ask for a success probability equal to 1, whereas in non-deterministic polynomial time solvability, it's still okay to only have a strictly positive success probability. Both separate or allowed to separate from a success probability 0, but polynomial time solvability just asks more. Okay, so the non-deterministic polynomial time algorithm solves this NP problem, or we say it solves the NP problem already when the success probability is strictly larger than 0 if and only if the instance was a yes instance. Another way of thinking about it is that the non-deterministic algorithm has this guessing device that allows us to guess the right certificate among the set of certificates. Okay, so now that we have defined the complexity classes, P, NP, and co-NP, we still would like to say something about the potential difference between those problems in P and the problems in NP. So those problems that have a deterministic polynomial time algorithm and the problems that probably only have a non-deterministic polynomial time algorithm. And in order to do that, we come to the arguably sharpest blade that complexity theory actually has, and that is the concept of problem reductions. Okay, so the definition is as follows. We say we have a polynomial time reduction from a decision problem by 1 to a decision problem by 2 if we have such a mapping phi that maps instances from problem 1 to instances from problem 2. Okay, and it has to fulfill two properties. First of all, the mapping can be computed in time that is polynomial in the input size. So phi of I1, when I1 is an instance of problem 1, phi of I1 is an instance of problem 2, and that can be computed in time that is polynomial in the encoding length of instance 1. The most important property is that this mapping maps yes instances to yes instances, and that is an if and only if. So if I have a yes instance of problem 1, then this is a yes instance of problem 2, and that is if and only if. Also, if phi of I1, so the image is a yes instance of problem 2, that has to be a yes instance of problem 1. Okay, so it's important to have an if and only if here. So yes is mapped to yes, but the mapping actually goes in one direction only. Okay, it's not a bijective mapping. And then once we have such a polynomial time reduction from problem 1 to problem 2, we say pi 1 can be reduced to pi 2, and we, in writing, this is expressed by this kind of curly small or equal sign, with the idea that this problem is in some sense smaller or less difficult than this problem, or in other words, this problem pi 2 is at least as difficult as problem pi 1. Okay, so let me illustrate this definition or support this definition by a little picture here. So if we have all the instances of problem 1 on the left-hand side and all the instances of problem 2 on the right-hand side, we map yes instances to yes instances, and that is if and only if. So that means no instances are mapped to no instances. Okay, so the two properties that this mapping phi has to fulfill is first of all polynomial time. So we have to be able to execute this function here in polynomial time. So for any instance here, the corresponding instance from problem 2 has to be computable in time that is polynomial in the original coding length of that instance, and that for all the instances here. And as yes is mapped to yes, if and only if, that means that no is also mapped to no. In general, this mapping need not be surjective, neither injective. And for most of the reductions, say non-trivial reductions, this will also be the case. Okay, so let me give you one little example of a problem reduction. And that is, we are now reducing the problem click to the problem independent set. Okay, remember what was the click and the independent set problem? Given a graph, a clique in the graph is a set of nodes that are pairwise connected, and an independent set would be a set of nodes which are pairwise not connected. So in this graph here in blue, that would be a clique, actually a maximum clique in that graph. And in red, you see an independent set, and I think it's also a maximum independent set in that graph. Okay, so back to our mapping. So we want to reduce the click problem to the independent set problem, okay? And we are talking about a decision problem. So the question, or the problem number one, decision problem number one, is the question, does there exist a click in the graph of size at least k? And we reduce this problem to the problem, does there exist an independent set in the graph of size at least k? And in this case, the mapping is, or turns out to be, a bijective mapping. But remember that this doesn't have to be the case in general. So here we define the mapping quite easily by just mapping the graph, the instance of the click problem, to an instance of the independent set problem that is also a graph, and we just map the graph to its complement graph, which has all the non-edges of the original graph, okay? And by doing that, you will see immediately that the click in the original graph is exactly mapped to an independent set in the image, right? So let us verify the two properties that a problem reduction has to fulfill. So first of all, it has to be polynomial time computable. That is actually the case. Computation of the complement graph, I just have to go over all pairs of nodes once. So that's a polynomial time computation for any instance of the original graph. And of course, if I have a click of size k here on the left-hand side, then that is exactly mapped to an independent set on the right-hand side. And if I have an independent set on the right-hand side, this will also be a click in the pre-image here, right? So I have a click on the left-hand side in the original graph G, if and only if I have an independent set in the image, which was the complement graph. And now the existence of this reduction, this problem reduction, from the problem click to the problem independent set, means that the independent set problem is, in terms of computational complexity, at least as hard as the click problem. So the idea is as follows: if I was able to solve the independent set problem, well, then I can also solve the simpler problem click. Simpler in the sense that that is the smaller problem of the two, right? So, or in other words, independent set is at least as difficult as click. And if I was able to solve this problem, then I will also be able to solve this problem. And let us formulate that in our most important theorem, maybe in this lecture. So if I have a reduction from problem 1 to problem 2, then a polynomial time algorithm to solve problem number 2, so to solve this problem here, the more difficult of the two problems, that also implies a polynomial time algorithm to solve the less difficult of the two problems, okay? So in that sense, problem 2 is indeed at least as hard as problem number 1. Okay, so let us briefly look at the proof. Okay, so this is what we want to show. If there exists this reduction from problem 1 to problem 2, and we assume we have an algorithm which is called ALK here to solve problem 2, the more difficult of the two, then we can also solve the easier of the two problems, problem number 1. Okay, so existence of this reduction means there exists this mapping phi, which maps yes instances to yes instances if and only if. What do we have to do? We have to be able to define an algorithm that solves problem number 1. What is that? That's an algorithm that returns yes if and only if the instance was a yes instance. Okay. How do we define this algorithm? This algorithm is called lec09 here, and it's just defined as the concatenation of the reduction and the algorithm to solve problem number 2. Okay. Remember that this reduction maps from instances to problem 1 to problem 2, and then this algorithm acts on problem 2. Right, so this is a correct definition. So let's see if this is really an algorithm that solves problem number 1. So first of all, if I feed it with a yes instance of problem 1, then by the property of the reduction, the image will also be a yes instance. Okay, and that means since we have an algorithm to solve problem number 2, so the image is an instance of problem number 2, and the algorithm correctly answers yes on that problem. So that was the algorithm that solves problem number 2. But this concatenation was the definition of our algorithm. So this is the newly defined algorithm, which returns yes on a yes instance. And also the other direction is simple. So if our algorithm, our newly defined algorithm, returns yes on some instance of problem number 1, then by definition of this new algorithm, that was the concatenation of the algorithm and the reduction, right? So I know that this concatenation returns yes, and by the property of the algorithm to solve problem number 2, that means that the argument here must have been a yes instance, right? This because ALK was an algorithm that correctly solves problem number 2. So the phi of I1 must have been a yes instance, and now we use the other direction. So yes instances are mapped to yes if and only if. So if phi of I1 was a yes instance, then also I1 was a yes instance. So in total, if our newly defined algorithm returns yes, then the instance must have been a yes instance. So that indeed means that this newly defined algorithm correctly solves the problem number 1. And it also does so in polynomial time, because this concatenation of the mapping is a concatenation of 2 polynomial time operations. Phi is a polynomial time mapping, and ALK is a polynomial time algorithm. So we have a polynomial time algorithm to solve problem number 1. So once again, if I have a polynomial time algorithm to solve the more difficult of 2 problems and there exists this reduction, then we can also solve the less difficult problem. And it's really important to realize that this mapping is a mapping, this mapping phi is a mapping that goes from problem 1 to problem 2, but not in the other direction, not necessarily. So that means that if I have a polynomial time algorithm to solve problem number 1, this problem here, and I have a reduction from problem number 1 to problem number 2, that there's nothing about the solvability, polynomial time solvability of problem 2, right? So if I can solve the easier problem, that doesn't mean in polynomial time, that doesn't mean that I can solve the more difficult problem in polynomial time. All right, so this is an important remark. And another thing that is important for the practical usability of such reductions is transitivity. So it's indeed the case that if I can reduce problem 1 to problem 2 and problem 2 to problem 3, then I can also reduce problem 1 to problem 3 and all that in polynomial time. So I'm skipping the proof for this lecture. It's just a very simple application of all the definitions, and it's contained in the lecture notes. So now that we can say something about problems which are more difficult or at least as difficult as other problems, we can define the hardest among the problems in the class NP, and that is the concept of NP completeness. Right, so the existence of a reduction says something about one problem being harder than the other problem, and now we want to define the class of hardest problems within the class NP, and that is the definition of NP completeness. So we call a problem NP complete if it's first of all member of the class NP, so the problem is contained in the class NP, and it should be at least as hard as any other problem in the class. So there should exist a reduction for any other NP problem pi prime to our problem pi. The second property is also called NP hardness. Okay, so a problem is NP complete if it's member of NP and if it's NP hard, so at least as hard as any other problem in the class. And frankly, if you think about this definition, it might seem totally impractical at first sight, because this second point here seems to be undoable. How can I ever show that all the problems in NP reduce to my problem? But of course, this works because of transitivity. I will come back to that in a second. First, let's have a look at the Venn diagram of complexity classes so far defined. So now we also defined the class of NP complete problems which is the hardest problems in the class NP. So for any problem which is NP complete, there exists a reduction from any other problem in the class NP to that problem. And notice that this also immediately implies that if I pick two problems which are both NP complete, they can both be reduced to each other. So in terms of computational complexity, they are equally hard with respect to polynomial time solvability. And this is true for any two NP complete problems, but it's not true for all problems in NP. In particular, as NP also contains the polynomial time solvable problems. Now, the maybe most important conclusion from this definition is the following. When I'm able to solve only one problem, which is NP complete, efficiently, so if I can solve one NP complete problem in polynomial time, then I can immediately solve all the problems in the class NP in polynomial time because of the existence of a reduction of all the problems to this NP complete problem here, right? So that's a theorem, an efficient algorithm to solve only one NP complete problem or only one NP hard problem. I don't even need membership in NP for that conclusion here. Then that yields that all the problems in the class NP would be efficiently solvable, so solvable in polynomial time, and that would exactly mean P would be equal to NP. And this conclusion is considered to be very unlikely, right? So you may know that there is a $1 million prize for somebody proving that P is indeed unequal to NP. Okay, so there's a strict separation indeed between deterministic polynomial time algorithms and non-deterministic polynomial time algorithms. But so far, such a proof doesn't exist, and the $1 million are still open. As a matter of fact, every year a couple of papers come out or are posted somewhere which claim to prove either P is equal to NP or P is non-equal to NP. And so far, all these papers have proved to be false. And if you're interested, I advise you to search for the homepage of Gerhard Wöginger, my colleague who is currently working in Aachen. He has collected some of these papers and some of the false proofs. But if you think you have solved the problem, you should probably submit your solution to the Clay Mathematics Institute to claim your $1 million. And I wish you good luck with doing that. Anyway, so what does this theorem give us? It gives us an important tool in order to justify why we are not able to find efficient algorithms for certain problems without being able to prove the non-existence of such algorithms. And that situation is very nicely sketched in this cartoon, which I took from the book by Gary and Johnson on computational complexity, by some people called the Bible. So the story is that your boss wants you to solve the Cumbersnatch problem for him, right? And then if you cannot solve, supposedly you cannot solve this problem efficiently, okay? And one of the strongest answers that you could give would be that you can say, I cannot find an efficient algorithm because no such algorithm is possible. Unfortunately, this is not the case for most of the problems. So such a proof is lacking. So what can you do? And you certainly want to avoid this situation, namely that you just have to say, well, I cannot find an efficient algorithm. Maybe I'm just too dumb. And what complexity theory and the definition of NP completeness gives us is a much stronger statement, namely, well, I cannot solve this problem efficiently, but neither can all these famous people here. And the idea is, of course, that because my problem is NP complete, or your Cumbersnatch problem is NP complete, I cannot find an efficient algorithm because if I was able to solve it efficiently, then all the other NP complete problems would be solvable in polynomial time as well. And all these famous people have failed to find efficient algorithms in the past 50 years for them. So that's not very likely to be true. So NP completeness is a justification for the inability to find efficient algorithms, but it's not the proof for the non-existence of efficient algorithms for a problem. It is a proof for the non-existence of efficient algorithms only under the assumption that P is unequal to NP. So the typical theorem that you will see in discrete optimization or discrete algorithmic optimization would be of the sort, well, this or that algorithm cannot exist unless P is equal to NP. And almost everybody believes that indeed P is unequal to NP, even though the proof is still missing. But let me come back to the definition of NP completeness once more, in particular to this for all quantifier here, since this for all quantifier seems to make this definition totally impractical, right? In order to show that my Cumbersnatch problem here is NP complete, I would have to show that all the other NP problems reduce to my problem, and that's infinitely many. So how do I do that? And the answer to that question is, well, first of all, we need at least one NP complete problem in the first place, and then we use transitivity, and that does the job. And what is this first NP complete problem? That is the famous satisfiability problem. So in the beginning of the 70s, Cook, Karp, and Levin showed that the satisfiability problem is indeed a problem that is in the class NP, and it's NP complete, so at least as hard as any other problem that can be formulated in this NP language. And I'm not going to do the proof here. Intuitively, it means that really showing that any NP problem can be formulated in the language of satisfiability, and that in polynomial time. And the existence of this first NP complete problem really helps, right? In the following sense, the only thing I have to show in order to show that my problem pi is NP complete, I only have to give this polynomial time reduction from the satisfiability problem to it. Because now by transitivity and by the fact that I know that this problem is an NP complete problem, I first of all know that all the NP problems here reduce to the satisfiability problem, and I just reduced the satisfiability problem to my favorite problem pi. And then by using transitivity, I get that all the other problems in NP also reduce to my problem pi. So in this sense, this really helps a lot, because I only have to show the existence of this one reduction from the satisfiability problem in order to get by transitivity the claim that all the NP problems reduce to my problem, and my problem is NP complete as well. And as a matter of fact, once I have showed that my favorite problem pi is also NP complete, that problem itself can again be used in order to show NP completeness of other problems. Okay, so it's not always that I have to reduce the satisfiability problem to show NP hardness. And here's a list of the first 6 problems that have been proved to be NP complete. And it includes well-known friends such as here the clique problem or the Hamiltonian cycle problem, for instance. And giving a polynomial time reduction of any one of these NP complete problems to my favorite problem also suffices to show NP hardness. So what is this mysterious satisfiability problem? In the satisfiability problem, we have Boolean variables called xj here, that they can be true or false, or 0 and 1. And a literal, that is a variable itself or its negation. And then we define so-called clauses, and that is the disjunction of literals. So here's an example of a clause called ci, the ith clause, which contains the literals x1, not x2, x3, not x4, and x5. And such a clause can be fulfilled by fulfilling any one of these literals. So this clause ci would be true if x1 is true, it would be true if x2 is false, and so on. And now a Boolean formula f in conjunctive normal form is just a conjunction of a bunch of literals. So in this case, m literals. So in order to fulfill the formula f, I have to fulfill each of these clauses, and inside the clauses, it is sufficient to fulfill one of the literals. Okay, so that's the satisfiability problem. It's a decision problem which asks, does there actually exist a truth assignment? So setting all these n variables either true or false, that evaluates this formula f to be true. Okay, so here is a little example. Here we have a Boolean formula consisting of 3 clauses, each of them consisting of 3 literals. And we are asking the question, does there exist a truth assignment for the variables that evaluates all the 3 clauses to be true? And well, for this little example, that is quite simple to see. So for instance, if I choose as truth assignment true, false, true, false for the variables x1, x2, x3, x4, then for example, x1 being equal to true already makes sure that the first clause will be fulfilled because of this literal here. x2 being equal to false fulfills the second clause because not x true will be true. x3 equal to 2 fulfills the third clause because of this literal x3 here. And so we have our list of truth assignments for the variables, the Boolean variables, which would fulfill these 3 clauses and hence the formula. So the question once again is, given such a formula with say n Boolean variables and m clauses, does there exist a satisfying truth assignment? Yes or no? It's a decision problem. And what Cook, Karp, and Levin showed is that you can express any NP problem in the language of such Boolean formulas. All right, so the example that I just showed you was already a very special example, namely that was a satisfiability problem where each of the clauses has exactly 3 literals, and that's known as the 3 satisfiability problem, a special case of the general satisfiability problem. And even though being a special case, the 3 satisfiability problem itself is just as mighty or as difficult as the general satisfiability problem. Because if you remember this picture, and these arrows here denote the existence of a polynomial time reduction, then the 3 satisfiability problem can be shown to be at least as difficult as the satisfiability problem, even though being a special case of the former. And also all these arrows denote existence of polynomial time reductions. So also this partition problem, for instance, is at least as difficult as the satisfiability problem, and so on. And if you think of the satisfiability problem itself, it already reads like a pretty general formulation of a problem, right? I still find it kind of astonishing, for example, that this problem here, this innocent partition problem, is also NP-complete, so at least as difficult or at least as hard as the satisfiability problem. So what is this partition problem? Let me define it for you. So in the partition problem, we are given a list of natural numbers, non-negative integer numbers, a1 up to an, and say the sum of them is even, okay? I'm just asking if I can partition these natural numbers into 2 sets, S and complement S, such that their sums is equal. So that's a very, very simple number theoretic problem, yet this partition problem is already NP-complete. So membership in NP is again clear here, because if you give me the subset that is a valid certificate for a yes instance, and proof of NP hardness I'm not doing in this lecture, but it can be done by reduction from any of the other known NP-complete problems. And the first proof that was given was from the NP-complete problem three-dimensional matching, actually, which has not been defined in this lecture. Now, as a final thing in this lecture, I would like to give you at least one non-trivial NP-completeness proof, and that would be showing that the clique problem is NP-complete. Okay, so remember, the clique problem is the question: given an undirected graph G, does there exist a clique, a set of nodes pairwise all connected with each other of size at least k? And the theorem I want to prove is that the clique problem is indeed NP-complete. That contains two statements, namely first, that the clique problem is a member in the class NP. So I have to convince you that there exists a certificate for yes instances that can be verified in polynomial time. But that is simple. That is in this case, again, just the clique itself. And the clique has size at most n, the number of nodes in the graph. And the question if it's really a clique or not can be simply verified in polynomial time in the size of the graph. So how do I show NP hardness? And here I use a quote by Christos Papadimitriou, also a very famous researcher who has written actually several books on computational complexity and algorithms. He once said in a lecture that I witnessed, well, real men reduce from satisfiability. And I think I should also say real women reduce from satisfiability. We know that if we show that one problem is NP hard by reducing some other NP hard problem or NP complete problem to it, then there also exists a reduction from satisfiability, right? Because all the NP complete problems are equally hard and can all be reduced to each other. So sometimes reducing directly from satisfiability can be a bit complicated or cumbersome, but at least we know it is possible for an NP-complete problem. And in proving NP hardness of a problem, we should, of course, make our life as easy as possible by choosing the simplest possible reduction that we can find from any known NP-complete problem. Anyway, here, the reduction from satisfiability is not even very complicated. So what we do is we give a polynomial time reduction from the three satisfiability problem. I'm not sure if that qualifies for this quote from Papadimitriou here, and we reduce the three satisfiability problem to the clique problem. Okay, so let me fix a little bit of notation. So M is the number of clauses in the three satisfiability problem, and N is the number of variables. And we will set up a proof that shows that the Boolean formula f, an arbitrary Boolean formula f, in conjunctive normal form is satisfiable if and only if a certain graph has a clique of size at least m. Okay, so this will be the result of the reduction. So the graph that we will define in this reduction will have exactly one node per literal of the satisfiability problem. So at the end, it will have exactly 3m nodes, where m is the number of clauses of the satisfiability problem. So in order to show NP hardness of the clique problem, we have to define this mapping, which maps instances of the three satisfiability problem to instances of the clique problem, right? So what we do is for each clause Ci, as I already said, we define exactly 3 nodes in the graph, exactly one for each literal, how it appears in the clause. I will show a figure in a second. And we introduce edges between these nodes only between literals of different clauses that belong to different clauses, and only if the corresponding literals are not the negations of each other. So we do not introduce an edge between two literals xj and not xj, right? So the computation time to set up this graph, so that is of course order m time to write down all the nodes, and at most order m squared time to write down all the edges, okay? And the claim that we are going to prove, once we have set up this reduction phi here, that the formula is satisfiable for the three satisfiability problem, if and only if in the image space, so that would be the image of such a formula would be this graph here. So the image of this formula, the corresponding graph, has a clique of size at least m. Okay. And here is the illustration of this reduction. So we have here the formula that I actually showed earlier, right? And we have introduced, for example, here in red, the corresponding 3 nodes in the graph. So that would be x1, x2, and not x3. Okay, and likewise for the other 2 clauses. We have introduced edges only between nodes in different color here, nodes that belong to different clauses. So there is no edges amongst the red nodes, there is no edges amongst the green nodes, and also no edges here. And we have introduced an edge between 2 nodes of different clauses if and only if these 2 literals do not contradict each other. So for example, here is a node which corresponds to the literal x1, and here is a node which corresponds to the literal not x1, and therefore there is no edge between these 2 nodes. But all the other edges are there. And now the statement of or the claim that I want to prove is that this formula is satisfiable if and only if I find a clique of size, well, number of clauses in this formula, in this case 3. So if and only if there is a clique of size 3 in this graph. And one thing should be clear, there can only be cliques of size at most m, or in this case 3 in this graph, simply because we have no edges amongst the nodes that belong to the clauses, right? Now there's 2 claims that I should verify, namely if there exists a satisfying truth assignment here, then there exists a clause of size 3 in the graph and also in the other direction. So for instance, pick a satisfying truth assignment, the assignment which makes all the variables true, x1, x2, x3, x4 equal to true, then I should be able to define a corresponding clique. So, but if x1 is true, x4 is true, and also x3 is true, right? Then I have found my clique, because the corresponding literals certainly do not contradict each other, right? And likewise, if I have a clique, an arbitrary clique in the graph, oops, no, this one, then this I can set the corresponding literals to be true correspondingly, and that will also give me a satisfying truth assignment. And as a matter of fact, there is several satisfying truth assignments for this formula. We have seen that earlier, and here is 3 examples of that. If you insist in a, say, a more formal proof, then let's see, if we have a formula which is satisfiable, we know there exists a satisfying truth assignment, x, that makes for each of the clauses at least one of the literals true. And I define a set of nodes in the graph by picking any one literal from the corresponding clause that this truth assignment actually makes true. And since this is a valid truth assignment which cannot contradict itself, all the corresponding nodes will be connected by an edge, and that defines my clique, because otherwise that would say that a variable xi and a variable not xi would be true at the same time, which cannot be for a valid truth assignment. On the other hand, if this graph that results from the reduction has a clique of size m, then as it's a clique, none of the corresponding literals are negations of each other. So therefore, it's okay to define xi to be true if xi appears in the clique, and to be false if not xi appears in the clique. And that will be a valid truth assignment for the formula, which it fulfills. So that finishes the proof that the clique problem is indeed an NP-complete problem. And recall that this proof consisted of two parts. The simple part is usually showing membership in NP, and the more difficult part is usually showing NP hardness by giving a reduction from some NP complete problem, in this case 3 satisfiability. But there is cases where actually we succeed in giving a polynomial time reduction from some other NP complete problem, but we do not succeed proving membership in NP. And also such problems are actually NP hard, at least as hard as any other NP problem. And I want to make that very explicit on the next slide. So the claim is that also problems outside NP can be at least as hard as any other NP problem. And here is one example. So if you consider the problem where we are given a graph and an integer number k, and we ask, does this graph have more than k different Hamiltonian cycles? Okay. So one can show that this is an NP hard problem, but the membership in the class NP is actually not clear. And that is because the only certificate that that I can think of at the moment, at least, is that I give you, for a yes instance, I give you the list of all the different Hamiltonian cycles. But that list could be exponentially long, as the number k could be exponentially large, right? So it's not clear how a certificate would look like that I would be able to verify in polynomial time. Nevertheless, it is an NP hard problem. It is at least as hard as any other problem in NP. Another class of problems that I would like to mention here is optimization problems. So an optimization problem P cannot be member in the class NP simply because it's not a decision problem. So it's not a member of the class NP syntactically. But nevertheless, we want to be able to say that optimization problems are NP hard. And the definition we can use here goes back to Alan Turing. So we can say that an optimization problem is called NP hard if a polynomial time algorithm to solve that problem would yield that P is equal to NP, or would yield that every NP problem can be solved in polynomial time. So also optimization problems can be as hard, or at least as hard, as any other problem in NP. So for instance, if you pick the problem down here, that of finding a maximal clique in the graph, if I would be able to solve that problem in polynomial time, then I will also be able to solve the corresponding decision version of the problem, which is an NP complete problem, so P would be equal to NP. Hence, this is an NP hard problem. Now that said, we can extend the Venn diagram of complexity classes that I had earlier, and namely extend it by this light red area here, which now contains all the NP hard problems. And so these NP hard problems are now problems that are potentially or syntactically outside of the class NP, but it also contains the NP hard problems which are member of NP, which is the NP complete problems. Okay. The important thing to realize is that a polynomial time algorithm to solve any one of the NP hard problems would immediately yield that all the problems in NP would be solvable in polynomial time, hence P would be equal to NP. Now that said, that really finishes this crash course in complexity theory, and I can only mention that there is many more complexity classes. Some of them are mentioned also in the lecture notes, for example, P space for polynomial space, which contains the class NP, for instance. And if you're interested, I would point you to the website of the University of Waterloo, which contains a whole zoo of more complexity classes. So now that we can tell what it means for a problem to be hard, or at least as hard as other problems, and NP hard and NP complete, of course, I mean, an NP completeness proof for your favorite optimization or a decision problem, or NP hardness proof of your favorite optimization problem, does not make the problem go away. So therefore, in the next or in the final couple of lectures, we will be talking about how to deal with NP-hard optimization problems, because the problems are still there and we want to find good solutions for them. So with this, I thank you for your attention and see you for the next lecture on approximation algorithms.